Okay, so now we'll do example 6.10. A baseball thrown vertically upwards from the roof of a tall building has an initial velocity of 20 meters per second. That will be upwards. Calculate the time required to reach its maximum height. Find the maximum height. Determine its position and velocity after 1.5 seconds and also after 5 seconds. Well, first we have the three independent equations, which I've written down to save a few seconds. And we need to think about our tall building. This is my illustration of a tall building. It's even got windows in it. Great. The ball is thrown from the roof, and we're assuming that that literally means from the roof, so somebody must be lying down on the roof to do this. And we need to make some choices about axis system. So we'll use the normal axis system, in which case remember that the acceleration due to gravity is vertically downwards, and therefore we need to give it the sign minus g. So to use any of those three independent equations, we will need to substitute minus g for the acceleration. We need to set a 0 for this problem, so we'll take the roof of the building to be y equals 0, in which case the motion of the ball will be vertically up until the potential energy becomes equal to the kinetic energy, and we'll talk about that later. Anyway, the motion will be vertically up, the ball will briefly come to rest, and then the motion will be vertically down. Okay, so that's the motion, and we're asked to find the point, some conditions about the maximum height. So at this maximum height, the velocity Vf will equal 0. So that's the condition for maximum height, and we can straight away substitute that into equation 3 to find the time which we are asked to compute first. So substituting into equation 3, we have that this is equal to the initial velocity plus the acceleration times the time, which is minus g, that's the acceleration times the time. So as the initial velocity minus the acceleration due to gravity times time equals 0, we can take gt over to the left side. So we add gt to both sides, and we find gt is equal to the initial velocity. Therefore time is initial velocity divided by the acceleration due to gravity. And substituting in, the initial velocity is 20 meters per second upwards. So substituting in for the value of g, this is 20 divided by 9.8, 20 watt, 20 meters per second divided by 9.8 meters per second squared. Meters per second cancel, per second becomes second on the top. So we're left with a time equal to 2.04 seconds. So this is our answer to part A, and being nice to the person who has to mark the problem, we will clearly indicate our result. Well, then we're asked also in part B to find the maximum height. So we're looking for an equation where we can use the information that we now have to find the maximum height. In fact, we don't need to use the time. We could substitute into equation 1 because we have the initial velocity, a time, the acceleration and a time. So that will give us the distance, but it is actually simpler in this case to use equation 2, which gives us the final velocity, the initial velocity, and the acceleration times the distance. So let's use equation 2 to do that. So we have that the final velocity squared is equal to the initial velocity squared plus 2 times the acceleration times the distance. In our case, the distance is y, and the acceleration is minus g. So we have v final squared is equal to v initial squared minus 2gy. So if we subtract the initial velocity from both sides, we have vf squared minus v initial squared is equal to minus 2gy. Divide both sides by 2g, and multiply both sides by minus 1. Then we have that the position y is equal to v final minus v initial over 2g. That is a general equation, and to use it to find the maximum height, we need to substitute the condition for maximum height, which is that v final is equal to 0. So at maximum height, v final is equal to 0, and therefore we have 0 minus vi squared is minus vi squared, minus vi squared is just vi squared. So our equation becomes vi squared over 2g equals y. And it is not just any y, it's now the y for maximum height. So we'll show that. So if we substitute in our numbers, we have 20 vi is 20 meters per second squared divided by 2 times 9.81 meters per second. And so we can see that meters squared divided by meters is meters, per second squared divided by per second squared is 1, so this will be an answer in the unit of meters. And putting those numbers into our calculator, well, first 20 divided by 2 times nearly 10, this is going to be very close to 1, but it's 20 squared, so it's going to be very close to 20. So 20 squared divided by 20, this is going to be close to 20, and plugging the numbers into our calculator, we find that the maximum height is equal to 20.4 meters. And I'm running out of space, so I'll put the y max on the right hand side and be nice to the marker and indicate that this is our result for part B. Okay, so we're rocking along now. We have the time for maximum height, we have the maximum height, and we found both of these by using the condition for maximum height that the final velocity at that point is 0. So now we need to find the position and velocity after 1.5 seconds and after 5 seconds. This is the easier part of the problem, so let's get to that. We'll use our independent equation 3, and so we'll write that as v final is equal to v initial plus acceleration times time, and acceleration is minus gt, so we can write this as v initial minus g times time. So for the various times, this will give us the velocities. So can calculate the velocity at t equals 1.5 seconds as being equal to the initial velocity, which was 20 meters per second upwards, minus 9.8 meters per second squared times 1.5 seconds. And plugging those numbers into our calculator, we find that the final velocity at t equals 1.5 is equal to 5.3 meters per second. And clearly we can calculate the other time in precisely the same way. So if we substitute in 5 seconds instead of 1.5 seconds, we will find the final velocity corresponding to t equals 5 seconds, and numerically we'll find that that is minus 2.9 meters per second. So after 5 seconds, that tells us that the ball is traveling in the downwards direction. Now I think I might have pressed the wrong button on my calculator, so let's just do that by dead reckoning. Let's go back and look at this equation. So if we actually have 5 instead of 1.5, then it's approximately 20 minus 10 times 5. 20 minus 50 is minus 30. So I did make a mistake. That should be 29 meters per second, not 2.9. So always good to check. Right. So the last part of the problem, C and D, is to determine position. Well, we've determined the velocity, we can determine the position, and we can determine the position using distance is equal to initial velocity times time plus a half at squared, which in our case becomes minus a half g t squared. So the initial velocity we know, the time we are given, the acceleration due to gravity we know, and the only thing I need to do is to point out that this is equal to our position y. So I can get rid of the general statement for position. Okay, so that's the equation we need to use. All we need to do is plug in the numbers and do the calculation. So we can calculate y for t equals 1.5 seconds, and plugging in the numbers we get y at t equals 1.5 is 19 meters. So that's positive, so that is a height above the roof, and similarly we can calculate y at t equals 5 seconds, and when we plug in the numbers we will find that that is equal to minus 22.5 meters, which is below the roof. So let's just couple together the two which belong together and point out that the velocity at time is 1.5 and the distance at time equals 1.5, and those two together are part C, and I have the luxury of an infinite number of colours on this computer, so we'll also point out that the final velocity at 5 seconds and the position at 5 seconds are coupled together, and this is part D. And we're done.